Let's quickly review the types of the systems and problems we deal with and see which one is complex, which one is not. The first one is the category that is called simple. In the previous videos, we talked about classic mechanics type of problems. These are the one or two variables, very simple systems with linear problems. We call them linear Newtonian systems. And we have tons of those, and most of the traditional science that we have is focused on simple systems, and most of our advancement in our lifetime, in fact, whatever we see around us, 90% of those are coming from these systems and handling the situation with these systems. These are the simple problems, require simple solutions, and we can handle it. In fact, for simple problems, we prefer simple solutions. The second group of problems or systems are complicated systems, also known as disorganized complexity, like gas molecules. These are not two variables. These are trillions and millions and billions of variables and components. They are very disorganized, almost purely random in behavior. And interestingly enough, these can be also handled with the same techniques and statistical methods and things that we learned in scientific methods studying various phenomena. So simple system methodology is applicable to complicated and disorganized systems methodology as well. In other words, disorganized complexity can be studied with statistical terms. And then we have a third group of problems. We call them complex problems or complex systems, which are organized complexities. These are different stories. They have interactions and they are interrelated. And for the sake of that interaction interrelated, they show non-linear behavior and they have emergence property, which means they show a behavior in system level that is not reducible to component level or interaction level. As a result of these principles, these systems and these problems cannot be studied with traditional methodologies in statistical science. Why? I give you only two reasons. There are many. One, superposition or homogeneity. One or both of them fails when we have nonlinearity. And both of them are explained in the text, what is superposition and homogeneity in a mathematical function. In nonlinearity, one or both of these conditions fail. And therefore, having a form of normal type of distribution is very rare. We usually see power law distributions in these systems. I have another video about power law that you can watch. And therefore, traditional statistics is not going to help, because most of the time what we use as mean or standard deviation in a Poisson distribution, a Gaussian distribution that we use in traditional statistics or statistical mechanics, fail to work in case of power law distributions. Therefore, we cannot use traditional statistics. Another thing is that almost all of the statistical methods that we have in our toolbox to study complex systems have an assumption, an important assumption, simple but important assumption, and that's independence of observation. So we randomly sample a group of people, a group of things, and we study that. And with that random sampling, we can generalize to the entire system our finding because we are observing them independently. In complex systems, because of that level of interaction, high level of interactions, in fact, we shouldn't assume independence of observation because they are highly related. So that independence of observation cannot be applied to complex systems. Therefore, we should study the entire system. And if we want to study the entire system without sampling that are interrelated to each other, these components are interrelated to each other, traditional statistical techniques, including statistical mechanics, are not going to work well. Remember, in the first week we talked about applicability of reductionistic approach to studying complex systems. We are not saying complex systems cannot be studied using reductionistic approach. In fact, you are going to see we use a lot of statistical mechanics in studying entropy and information systems, information theory, which is for complex systems. But what we are saying is it's not enough. reductionist approaches are not enough. Therefore, we need a new mathematics. We need a new comprehensive approach to study these systems that is for complex systems, that is not applicable for the other one, and it's based on holistic perspectives. In one of your readings, it offers 4 different categories of problems. I do not agree with that. That's why I'm showing it here. So it says order to the right, disorder or unorder to the left. Introduce the first form of problem, simple problems. We talked about it. It's the same thing as simple systems. And then it introduces complicated. So this is the first mistake I believe they make. Complicated is in the order side. Complicated is in fact very disorganized. That's why we call it disorganized complexity. So that's the first problem. And complicated problems or systems are the systems with billions and millions and trillions of components, but since there is no interaction basically, still we can use the simple method we use for simple linear Newtonian systems to study complicated system. And these two together forms about 90% of what we know in the history of science. And then it introduces the complexity part of the story, which is again is the organized complexity. We talked about it. And then it introduces a 4th category known as chaotic systems. Now, chaotic systems are not necessarily a separate category of the problems. Chaos theory, which I'm going to explain in one of the videos where I'm talking about the attributes of the systems. Chaos theory is a subcategory or is a specific problems or systems under dynamic system theory. So a specific group of dynamic systems are called chaotic or chaos theory. That is closely related to the complexity. In other words, these 2 categories of complexity or complex systems and chaotic systems are one. They are not 2 separate, and they are closely related. In fact, you are going to see that chaotic systems have deterministic roots. They follow a very specific deterministic rules that create these systems. However, because of the sensitivity to initial conditions, or also known as butterfly effects, the outcome is unpredictable because of the error magnitude, basically. So yes, that's one thing I wanted to, because you're going to read the text, I just want to make sure that you understand that chaotic problems or chaos system or chaos theory, which is a subcategory of dynamic system theory, is not a separate group of problems and systems. It's rather closer to the complexity. You can put them into the same group. Now, what's the purpose of talking about all these systems? We already know that complex systems have different attributes. We talked about 15 of their features and why we should care about this. And there's one simple reason known as Cobra Effect. The Cobra Effect has a story that happened in India. Back then, in the time of colony of the India being dependent on UK, basically British Empire ruling the country. So British people are not used to seeing cobras and having this snake around. It's not basically a snake that you can find in UK. And being poisonous these creatures are, they were really afraid of snakes and they didn't like it. So basically they want to get rid of the snakes. And India is one of the countries that basically is the home for cobra snakes, which is a very poisonous snake. So what they did, they come up with a solution, and this solution is very interesting. They offered money. They offered money for everyone who bring cobra snake, dead or alive. In case of alive, they are going to kill it. And they put incentives. And Thinking was, if we offer money, if we offer reward for people catching and bringing cobras, and that's money is a good deal of money, wholesome money, which is nothing for us, but it's a large amount for the locals. We are going to get rid of the population of cobras because these people are going to catch them, bring it to us, dead or alive, and we are going to pay for that. And over time, the population of cobras is going down. This is a very simple solution, not elegant necessarily, but very simple solution. And you might think it works, yeah? Well, the habitat issues are complex system problems, and usually human dealing with animals or larger ecological systems that human is part of the story is becoming even more complex. Consider this animal habitat as a complex system, human habitat is a complex system, human itself is a complex system. I'm not sure if you can consider snake as a complex system or not. Most definitely you should. Snakes are complex systems, and then we are finding a solution for the interaction of these two complex systems, and we think of a simplest solution we can. What happened is that population of cobras, in fact, increased in India. Why? Because it's not easy to find and catch a cobra, but it's very easy to have a farm of cobra. You start your own business farming cobras, and you take care of them. They lay eggs, and you have more cobras, and you create more of this, and then you start selling it to the British. And it sounds a very profitable business. And therefore, because of that reward and money they were paying for cobras, people started farming businesses, farming cobras, and when the news get to the British that the money they're spending is actually spent on creating cobras rather than eliminating them in the nature, natural reaction is what? To stop paying for that, right? So they get rid of that incentives and rewards, and they are not paying anymore for any of this. So now you have a farm with tons of cobras in it. You're breeding them, and then nobody's paying for them anymore. Suddenly, this is not a profitable business to have. Every day that you take care of these cobras, it's a financial burden for you. So what's the natural reaction of you? Either kill them all, which some of them did, or release them to the nature because you don't want them anymore. Now, even killing them is going to have cost, especially in large sum. And this is a poisonous animal. It's not easy to deal with them. So killing cobra is dangerous when they are not paying for it. If they were paying, you were killing. They are not paying for it, so you don't want to risk your life, or the people that you don't want to risk their lives to work for you for killing the animal. Therefore, the cheaper solution is to release them into the nature. So what happened as a result of that simple solution they come up with? Population of cobra increased in India. So the moral of this story is that simple solutions are not always the best solutions. If you're dealing with complicated problems or simple problems, yes. The more simple the solution is, we can call it elegant. We have examples of these elegant solutions in science and physics. You can find tons of those, like Einstein's E=mc² equation is a very elegant solution, a very elegant equation for a problem. We have Euler's identity, which in my view is the most elegant equation in all history. It's about series using both pi number and e, natural number. So yeah, we have tons of these in mathematics, physics, chemistry, and in entire science. We have tons of these simple solutions that are very elegant. But the problem is, in complex systems, not that always they fail. Sometimes they are still successful, and obviously if they are, we prefer always simplicity over complexity. But complex systems complex problems not always being solved with simple solutions. Sometimes, in fact, it make it worse. So sometimes complex problems require complex solutions. That's the moral of the story. That's why we need to understand what problem is not complex problem, what problem is complex problem, what are the attributes of complexity that we're talking about in order to be able to basically find a solution for those. Now, the last thing that I want to talk about here is that we talked about from types of systems, types of problems, and we talked about 15 most important attributes of complex systems or features of complex systems. But I did not define complex system. Why? The reason is simple. Definition of complex systems is very difficult. So basically, if I want to define it, it goes like this. It's complex systems are type of systems with numerous number of components and interactions that are mainly disorganized and may have diversity, may have this, may have this, may have this, 15 may haves. Is the definition of complexity, which is not a very good way of defining something. So I gave you the features of complex systems. I gave you the types of different systems and problems, and I leave it to you to define it for yourself. In fact, one of the readings that written recently after the Nobel Prize for a climate study by a physicist that is considered as the first Nobel Prize in the complex systems or complexity science. As a result of that, a recent article asked 18 prominent complexity science scholars to define complex systems and talk about some specific questions. It's a very interesting reading, and I strongly suggest to read that carefully, because while they're defining, they talk about some of these attributes and features of complex systems. And you're going to see that if we have 18 different versions of the problems, there's a huge overlap. And that overlap is the area that we are living in. But there is no single good definition. And they refer to some of those 15. In fact, I believe you can find 10 of those 15 features we talked about in their definition, not again in a single definition, in the collective of those 18 definitions. And in fact, you are going to see some contradictory approaches even defining these systems. Like, for example, when we talk about fragility, which is a result of adaptation and being more efficient versus robustness. So which one is? Complex systems are so fragile or so robust? At the same time, both. So which one is? Complex systems have order, spontaneous order, or they are disorganized, disordered? Both of them. So these are some of the contradictions, and the most important contradiction you are going to see when reading that piece is that some of those 18 scientists in fact use reductionist approach to study complex systems. So from even more ontological and epistemological perspective, you're going to see some contradictions. Some people still want to talk about predictions, talk about explanation, use reductionistic approach, break it down to smaller pieces and then study that, while some others talk about holistic approaches and new mathematics that we need to study these systems. So I strongly urge you to study that paper, and with that, hopefully you are going to define your own definition of complex systems. Again, it's not going to be a formal definition. It's not going to be even a good definition, but it's going to be your definition, and you're going to understand complex systems based on that. So it's kind of going to emerge as a result of all those readings that I have provided. So hopefully the definition is going to emerge to you. It's going to reveal itself to you. And then you are going to use that to define or identify what is complex problem, what is not.